Hey gang, welcome to Computer Graphics. Today we're going to talk about the next assignment. We're also going to, I think, take a little time and look at my code for assignment 2. I'm kind of worried about the code at some level for that some people turned in. Most people did well on the programming assignment. They got the points. But when I look at even at assignment 2, how a lot of the code is just kind of glued together with sticky tape, it starts to make me kind of nervous because I know what's ahead of you guys for assignment 3. In fact, over the Martin Luther King Jr. 3-day weekend, I implemented assignment 3. And I keep telling you guys how long it takes. It took me about 20 hours. But I was like writing the algorithm while I'm writing the code and debugging it, and I'm going to provide you guys with the algorithms. So your job is maybe 25% as hard as the job that I took on myself. That said, the algorithm we're going to talk about today, polygon filling, it's not hard to understand, and it's not like it's hugely long. It's not. I think my core algorithm fit in, it fits on a page. The core algorithm does, with comments and blank lines. So the whole thing is probably, the core algorithm is probably 25 lines long, but they're delicate. It's easy to, even if you're just transliterating it, if you're taking the algorithm and just turning it into code, it's easy to make a little mistake. And then the thing is okay, debugging it. It's not writing the program, it's debugging it that takes a long time because it's very delicate. So even though I'm giving you way more to work with than I had, it's not going to be a 1 hour or 2 hour thing. So don't think that. You really need to budget, like I keep telling people, between 20 and 40 hours, which means really you should start on assignment 3 yesterday. Okay. All right. Let's see. All right. Well, we gained a person, so we're now at 15. That's good. Okay, so why don't we start by looking at my assignment 2 code. Now, I fully and firmly admit that my code for this is not at all, awesome code by any stretch of the imagination. It is not object-oriented where it should be object-oriented, but my goal in this class is to teach you the algorithms, not to worry about object-oriented programming. And so for that reason, in other words, I would rather the algorithms be more straightforward and not put a lot of stuff around things, so that the algorithms and the procedures are obvious. And that leads to a lot of code that makes me kind of want to barf. But when I look at some of you guys' code, I go, oh, mine's not so bad. Okay, so this is assignment 2, right? Our canvas, our distance D, and we've got our objects. We've got our old initial polygon, a pyramid made of 5 polygons: the apex, base 1, base 2, base 3, and base 4. Those are our points, and then from there we get a front poly, a right poly, a back poly, a left poly, and a bottom poly. And then from there we define a pyramid as consisting of this polygon list, and we also have a vertex list for the pyramid, which we're calling a point cloud, because that gives you, it reinforces the idea that there's no order associated with these points. Like I said, this is what I'm calling point cloud. Most people call vertex list. But when you say vertex list, that makes you kind of think of there's some order to the list. And by calling it a point cloud, I'm making it clear there's no order associated with these points here. The order comes in the definition of the object as a collection of polygons, where each of those polygons is a ordered list of points. All right, so that's why I'm using the terminology that I'm using. Also, define a cube. It's got 4 points. It's got 8 points, 4 points on the top, 4 points on the bottom. And then it's got some polygons. It's got a top poly, a front, right, back, left, and bottom poly. So the cube is this collection of polygons. The cube point cloud is, of course, all of the 8 points, the 4 points for the top, the 4 points for the bottom. And here's something that would have made a lot of you guys' lives a lot easier if you had done. I save off my point cloud. So I've created my point cloud here, and then I save off a copy of that point cloud in something I call default cube point cloud. And it's a deep copy. A deep copy in Python is what it sounds like it is. It's a copy of the entire structure. It rebuilds a new structure that's identical to the other structure. So all of the my point cloud, right, is a list of these 8 points. Well, now my cube point cloud will be a copy of this structure. So it'll be obviously at a different location in memory, but it's identical in the values and the pointer structures. So every time I defined a point cloud, I did this, if you noticed up here, I did this also with my pyramid, right? So I'm making deep copies of these things. And then I create a second cube. So this is my third object, and it's actually just a copy. I offset it, but I'm rebuilding everything. Now, if we were using object-oriented programming, we would be able to instantiate cubes and instantiate pyramids, and that's the way you really ought to do this, rather than the kludgy way that I'm doing here. But at least you can see the structure the way I have things here. Okay, so after we've got our scenes, our polygons, we need to define a scene, because now originally for assignment 1 we just had one pyramid, right? So that's all you had to worry about rendering was that one pyramid. But now we've got a scene that consists of multiple objects. So I define a scene as a list of objects, all right? So a list of polygon, cube, and cube 2. And so there's also a point cloud for that scene. That's all of the points in the scene, right? And I make a default, which is just a copy of. So I make a scene point cloud. So it's got my pyramid point cloud, my cube point cloud, and my cube 2 point cloud. And then I make a default point cloud, because these are S's, because they're point clouds, a default pyramid, default cube 2. And so now basically by having these defaults, when I want to reset things, it'll be a lot easier. I also have a global variable called active object index, which is the active object. Now, how do I reset an object? So before I look at the reset function, let's look at how it's called. So when you hit the reset button on my interface, come on, Michael. When you hit the reset button on my interface, I call reset object on scene point clouds subactive object. Okay, so you know, active objects is either, it starts out at 0, right? So it's either I've got 3 objects, so it's either object 0, 1, or 2. So whatever object is currently the active index points to, reset object, you're passing it the point cloud for that object. Just the point cloud, because you don't need to know the structure. You just want to get the points back to where they were originally. And so scene point cloud subactive object is like the pyramid cloud or the cube cloud or the cube 2 cloud. That's the cloud. And then I'm also passing the default points cloud for the same active object index. So I'm passing the object that I want to reset and essentially the original point list, the default point list for that object. And since I have both of those things, resetting the object, you don't go through, you know, a million different individual point resets. You just say, okay, I've got the object, I've got its default. So for I in range length of object, that moves me from the object is the list of polygons. So this will be for each polygon, and then within a polygon, right? You will have well, I'm passing it an object, right? And within, which is a point cloud. So this is a list of points. Right? I'm passing it an object, which is a point cloud, which is a list of points. So for I in range length of object, this is how many points do you have in this particular point cloud. And then for each of those points, since a point has an X, a Y, and a Z, you let range go 0, 1, 2. And so then you just say, well, whatever this object is, I, that's the active object index. So it's 0, 1, or 2. It's the polygon, it's the first cube, or it's the second cube. And then J is just the X, the Y, or the Z. And you set it to default, which was the deep copy that you made, right? The default. And, you know, same list of points and X and Y and Z. So just this little bit of code here, I don't have to go, you know, like a lot of you guys had a switch to say, well, if it's a 0, it's going to be the pyramid point cloud. And then you would go like pyramid point cloud 0, 0 equals blah. Pyramid point cloud 0, 1 equals blah. Pyramid point cloud 0, 2 equals blah. Pyramid point cloud 1, 0 equals blah. And you unwound the whole thing into about, you know, 25 or 30 statements here. We can do a lot better than that. Okay? So I'm just trying to show you there are even when we're not, even, you know, if you're not getting crazy on object oriented, you can still make things a lot funnier. The next thing you have to do is you have to calculate if you want to. Well, let's look here. Let's talk about all of our operations, like scale in place, rotate in place, etc. Let's go to rotate in place. Rotate in place is Z. So this is a Z-axis rotation. What do you do with the Z-axis rotation? Well, you're given an object, which is going to be a point cloud for a particular object, either the pyramid, the cube 1, or the cube 2, and you're getting how many degrees you want to rotate that object. So you have to compute the center point of that object, the visual center, and then that's going to be to get you to the origin. And then the negative center point, it's just whatever the center point is, which is an X, a Y, and a Z, where it's minus X, minus Y, minus Z. I wrote a little function that multiplies a scalar times a vector to do that. It would really be just as easy to say minus center point 0, comma, minus center point 1, comma, minus center point 2. And that gives you your X, Y, and Z. It's a little straightforward. But then here's the core. Here's the core. Translate your object by the negative center point. Rotate your object around Z at some number of degrees. Translate your object back. That's what rotate in place does. And it uses the rotate Z from assignment 1. I mean, it uses the translate from assignment 1. So it uses those non-in-place operators, but it just now wraps it up into doing these three things. I saw some of you do things like, well, when you press the button, you do a translate, and then you do a rotate, and then you do a translate back. Or I've seen some of you take your rotates and muck with the interior of rotate to do the translate, the rotate, and then the translate back. You can do that, but it's a little more clear if you build a function on top that uses our existing translate, rotates, and scales. Okay? But all of these things depend on being able to calculate the center point of the object. Most of you did that. Some of you didn't. How do you calculate the center point? Well, I set my X, Y, and Z mins and maxes to the value of the first, to their values in the first object. I could have cut this down to 3 lines by using a loop here. Same thing. I now compute the X max, X min, Y max, Y min, Z max, Z min, and yeah, I'm doing it like that. I could have put this in a little loop that went from, in range 3 if I had wanted to. So yeah, I could collapse these a little bit, but they're short enough that it's not so crazy. And then once you got the mins and the maxes, you do your center calculations like we showed in class, and you returned the center point. You return center. So that's how we get our center point. And that's really pretty much the whole program right there in a nutshell. Render scene. You have to be able to draw all your objects in the scene. Now, if you didn't have to highlight in red the active object, you could have just said something real simple like for object in scene, draw object, object. And that would have been the whole render procedure. But we have to add a little kludge here so that we can highlight our active object in red. So it's a little longer for I in range length of scene. So how many objects do I have? I'm going to iterate over the objects. If my active object index is equal to I, then okay, draw this particular object, scene sub I, in red. Otherwise, draw the object in black. So that's that. Draw poly, draw line. This is all the same. Project is the same. Oh, make a note that when we talk about polygon filling today, I changed the polygon projection for Z, which we don't use, so it doesn't affect anything. I went ahead and made it consistent with our X and Y, so I changed this to be D times 0.2 over distance. I did that so that our Z values won't be between 0 and 1. I was getting worried about round off errors. So by multiplying them by the distance D, the numbers will be bigger, and you have to worry less about round off. So that was reset. Oh, and the last thing you have to do is you have to be able to move between objects. So what I did is I used the left and right keys, arrow keys. You need to do a root.bind to a key. And when a key is hit, that you call key pressed. And so here's our key pressed function. That's called whenever a key is hit. Our active object index. I have to say, here's another little thing that some of you haven't discovered yet about Python. And I had to relearn it myself because I don't use Python very often. You can access global variables within methods. And Python is happy to let you access global variables within a method. But if you go to set the global variable, you must have declared it global within your method, or else when you do an assignment like this, active object index, blah, 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 that'll be a local active object index within the key pressed method. And when you leave the method, it won't, your global active object index won't have changed. And I had some of you telling me, well, I couldn't get it to work. I couldn't get it to work. I kept changing it, and it would never change. Well, that's because you weren't declaring the global variable global in your method where you were changing it. Okay? So if you want to change a global within a method, you have to say global, the name of the method, the name of the object that you're going to change. If you don't do that, you can still access it, fine. But if you go to change it, you'll be building a new one within that method. So if our event key symbol, this is just the event you get from a key press, you can check, it's an object, so you can check its attribute key sim, or call the method key sim. And if that's left, the left arrow, then you want to subtract something, because left arrows go backwards. So I want to take my active object index and subtract 1 from it. That's what I really want to do. But before I do that, I've got to check to see if I've reached 0, because if I've reached 0, I then have to restart it at the biggest active object index, valid index. Same thing if I hit the right key, I want to add 1. That's the default, add 1. But you got to check to see if it's already at the maximum value, and if it is, you reset it to 0. So that's how you roll around. And notice, I built this, even though I'm not using object-oriented, I built this so that this works on any number of objects, right? And I built the render method, right, so that it works, or the reset, it'll work on any number of objects in your scene, right? And the reset is built so that it can reset any object. It doesn't refer to an object's name, right? So if you want to add objects in my little program, no, it's not nearly as good as if I had done it the right way and made it object-oriented. But if I wanted to define another object, I could define another pyramid, for example. Yeah, I'd have to go through and define its points and all that crap. But then I would just drop it in the scene point clouds, right, and in the scene. So really, I would just need to define it and then change these 3 lines of code, drop in the next object here, drop in its point cloud here, and I'd have a default value for it. I'd drop it in there. You do that, and now it works. So no, I didn't do it the right way. I didn't do it the object-oriented way, but I did it in such a way that there's still a lot of flexibility. Okay? And that's what you guys need to do. And it does all work. If you run the thing, you can move objects. You can move objects up and down and all around, and the whole thing works. And if I hit an arrow, I can move my little thingies.
Dr. O'Neill, I don't think you're sharing the program window.
Oh, I'm not sharing the program window, so you can't see it. But it looks just like all of the things you've seen. Let me, but to be a good little guy, let me go and share that window. Boom, boom, boom. See it in all of its little glory. One little thing I will do is I will let me show. So, assignment 3. Assignment 3 is going to require that you do 3 things: backface culling, polygon filling, and Z buffering. You should go ahead and implement backface culling today. That one's fairly short. You need to get it done. And you also need to get started on the polygon filling today. It'd be better if you got started on this assignment yesterday. But if you, but I don't know if that's possible unless you've got a TARDIS. But if you look at this, this is just with backface culling on, all right? And so you can see that my objects now look, you know, more solid, all right? The back faces aren't being drawn anymore, all right? Now, you might say, okay, well, this looks good, and it does, thank you. But it's not full, it's not full hidden surface, because if I go, it looks hidden, it looks like it's like these are solid as long as they don't overlap one another. But as soon as I go left, the gig is up, because you see, oh, you can still see through the pyramid. You can still see the cube, right? So backface removal is step one, but it's not by any stretch of the imagination the whole thing. So, okay. So I've shown you my code. I've shown you backface removal running. Let's look at the assignment. So this assignment is due on the 4th of February. You might say, oh, well, it's only the 20th of January. That's long. It's not far away at all, okay? This is an individual assignment as opposed to a team assignment. First thing you do, correct any problems with assignment 1 and assignment 2. That's the reason why I spent 30 minutes going over my assignment 2 code, is to give you ideas if you know, on ways to clean up your code. You know, some of you, your programs look even better. There are a couple of you whose programs look better than mine because you took the time to actually make an object-oriented implementation, which is good, and I encourage you to do that after you get the core algorithms running. But the vast majority of you had code that was worse than mine, which is actually kind of scary since you guys program and I never program anymore. So that kind of shocked me, which is why I felt like I should at least show you my code. Implement backface culling. We gave the lecture for that last week. In other words, do not render polygons. Am I sharing this? No, I'm not sharing this. Hold on a second. I'm talking about it, and I'm thinking I'm sharing it, and I'm not even sharing it. Sorry about that. There's a little green box when I'm sharing, and that's the only way I see that I'm sharing. So. Oh, we got another participant. We're up to 16. Okay, that's only about 5 people that are missing. Okay, so like I said, correcting problems with assignment 1 and assignment 2, implement backface culling that we covered last time. Implement polygon filling, we'll start talking about that today. In other words, add the ability to paint or fill individual polygons on a pixel by pixel basis. There is no way of accessing pixels in tkinter. Okay, it's built at a higher level than that. Okay, but you can simulate that by drawing a line that is 1 pixel wide. and that'll paint a pixel on the screen. And that's what we're going to do. We're going to use fill line, only it'll be like from XY to X plus 1 comma Y. And so that's how we will access our pixel, the pixel level. The result, however, is going to be slow. Slower than even I said slow there, because we're using a high-level line draw command to paint a single pixel, rather than being able to actually go and directly set a pixel, which would speed things up by several orders of magnitude if we had access directly to the pixels in the image buffer, but we don't. Okay, so that's what you're going to do there. We're going to have, I showed you how to bind keys because I specifically want you to bind the number 1 to the render mode wireframe only. So just draw edges. And so when you're just drawing edges, it's going to look like what I just showed you with backface culling, because wireframe doesn't respect isn't filling, and it doesn't respect Z buffer. So what I just showed you running is how your program will look when it's in mode 1. When you're in mode 2, you're going to do polygon filling followed by drawing the wireframe. So you will fill the polygon, then you will draw the wireframe on top of it. And that's sometimes helpful. That way, you know, when you switch between objects, you'll still have a red outline of the object you're manipulating and stuff like that. But if you really want to see the image properly without the edge lines drawn on top of things, you go to mode 3, which is polygon filling only. You just paint the polygons. You don't separately draw edges. They just get drawn as part of the polygon fill process. They just are part of the polygon. In order to make it easier for me to grade, because there's so many things that we have to discuss when we meet for our 15-minute slots, I want you to define the polygon so that the bottom poly is black, the front poly is red, the right poly is green, the back poly is blue, and the left poly is yellow. So by doing that, here you can see our pyramid. Obviously, you can't see the bottom of it, which is black, and you can't see the back of it, which is blue, but you can see that the front poly is red, and the right poly is green, and the left poly, if I can find it here, the left poly is yellow. Okay. Now for your cubes, I made the top of the cube be white, the bottom of the cube be black, and then the sides of the cube go from light gray through dark gray. So this is the darkest gray, this is the lightest gray, and these are you're looking at the back side of this cube. I rotate it, and these are the other 2 shades of gray. You can see the bottom of the cube is black. You can see the top of the cube is white. Okay? By using these colors, I'll quickly be able to see that you're projecting properly, that you don't have a surface normal backwards. I'll be able to see that the rotations are happening in the right direction. I'll be able to see a lot of things by everybody sticking to this coloring scheme here. Okay? Let me look. There seem to be a few questions. Is it going to draw like pictures used on DSL? I don't know what that means, Andrew. Do we have discretion on coloring other objects? Yeah, sure. If you wanted to define other objects, you have your discretion to color them however you want. You have to have at least 1 pyramid, and at least 1 cube, and I'll say at least 3 objects, so that I know that you've got a general way of moving between objects. So let's say 3 objects minimum. at least one pyramid, at least one cube, and the pyramid and the cube have to be colored the way I have here so that I can quickly test your code and make sure that it's working. So that is polygon fill. Now you might say, well, doesn't that completely solve the problem of making these objects solid, Mike? Because they're solid. Well, yes, but the order that I draw these polygons is pyramid, cube 1, cube 2. And then, since you can see that there are the outlines here, you can see the outline in red, I then go and paint the edges. So I fill the polygons, I fill the objects for pyramid, cube, cube 2. And then I go back, since I'm in mode 2 here, and I draw the edges for the pyramid, I draw the edges for the cube 1, and I draw the edges for the cube 2. Because I always draw the polygon, the pyramid first, if I were to move this pyramid in front of this cube, it would look solid, but there would be no way for me to take this cube and move it in front of this pyramid because they're drawn in the order pyramid, cube, cube. So if I move this cube over here, it will be behind this pyramid. Even if I change its z's by going move back, move back, move back to move it towards me, even if it's by z values in front of the pyramid, it'll always show up behind the pyramid because it's painted as pyramid, cube, cube. Right? You got to paint these things in some order. That's the order that I drew them, that I painted them. And like I said, even worse, the edges are drawn next. So like if I move this thing, you paint and then you draw and then you draw and then you draw the edges, and I'll show you why that could actually cause a little bit of weirdness. But let's look at what the Z buffer can do for you. This is what your program is going to do when you get Z buffer running. Here's the cube behind the pyramid. And now I start pulling the cube forward, and the first thing you see is the cube starts to merge through the pyramid. So the first thing that shows up is, since it's edge on, this corner of the cube is now pulled through the front of the pyramid. And then if I keep pulling the cube forward, more and more of the cube gets pulled through the pyramid, right? Eventually, if I keep pulling it forward, the cube will be completely in front of the pyramid, okay? So, well, let's see, Eric is asking, so is that the idea behind the Z buffer? And yes, I can pull things in, changing the order that objects are rendered based on Z value. Exactly. And then you say, oh, it seems that it's a bit different. Well, it's not. It lets us, if the cube is behind the pyramid, it'll be behind the pyramid. If the cube's in front of the pyramid, it'll be in front of the pyramid. The only interesting thing, well, and the whole thing's interesting, maybe the thing that seems a bit odd is that you can move one object through another. The whole object doesn't have to be in front of or behind some other object. It can partially occlude something. Now, normally in video games, we purposely make our objects solid to avoid these middle situations here. But sometimes for visual effect, we want one thing to pass through another. And this is just showing that hidden surface removal of the Z buffer is quite capable of doing this because it is computing depth on a pixel by pixel basis. So it is a general solution to the hidden surface removal problem. And it's the standard solution now that's always used. So you'll need to implement the Z buffer for general hidden surface removal. Now I have a little note here. I say, this should allow your program to handle general hidden surface removal for opaque, in other words, not translucent or transparent, opaque, solid 3D polygonal objects. Note that ZBuffer will only be effective when your program is in render mode 2 or 3, that is when the polys are being painted. So polygon fill has to be active. Also note, unless you manually re-implement create line, it will not respect the ZBuffer mode. What does that mean? I have line drawing turned off. This is mode 3 I'm showing here, not mode 2. Okay, I'm just filling the polygons, I'm not drawing edges. If I were to draw edges, the edge draw doesn't respect the buffer. So remember that I said that the order that I draw polygons is pyramid and then the cubes? This pyramid was drawn first and then this cube was drawn. Okay? The magic of ZBuffer allows us not to paint our cube in this region because the pyramid is closer than the cube face at this point. Same thing here, right? Same thing here. The white of the cube top is not being shown because the top of the pyramid sticks out of the cube here. So this is all visually correct. But if I were to go to mode 2, where I draw the edges, you would see edges, wireframes drawn over this thing, and you would see like a wireframe edge here and a wireframe edge here. The edge draw, the line draw, doesn't respect the ZBuffer. So it would look a little odd, is what I'm trying to tell you here. And Eric, you say here, well, rather, it's not just if cube Z is less than pyramid Z, then the cube is rendered over the pyramid, as in your original interpretation. What you said there is true on a pixel by pixel basis. It is not true on a polygon by polygon basis, because sometimes parts of one polygon might be in front of parts of another polygon, and sometimes the opposite might be true. There is not always a well-defined order of polygons. Now, we're not going to talk about it, but there are algorithms like Warnock algorithm that can be used if you can pinky swear that you'll never need to have an object pass through another object. There are algorithms like Warnock that tends to, it goes through and it whenever it detects that two objects are overlapping, it tries to find every polygon in the object and then figure out which polygon is behind which other polygon. But that still can be problematic, because what if I've got a polygon like this and I've got a polygon like this? They're not intersecting each other, but part of the polygon is behind and part is in front. So it's the problem, if you sit and you think about it, Eric, and when we go through the lectures, you can think about it, is not as easy as how you're initially conceptualizing it. Brian is asking, is this something you want us to change then so that the wireframe respects the Z buffering? No, don't worry about that. Okay. All right. So, Michael, you have taken up most of your lecture on these background tasks, and you have not started talking about polygon fill. And that's okay. We've got today's lecture and we've got Friday's lecture to get through polygon fill and Z buffering. Let's go to the notes. So mode 2, Andrew, I will demonstrate assignment 3 running. I'm not going to show you my code, but I will demonstrate assignment 3 running in real time during Friday's lecture. So you'll see exactly what it's going to look like. but I want you to get started now, because you can definitely do things like implement the modes. You can definitely do things like implement backface culling, etc. Okay? Okay. So let's go and share our lecture notes. Okay. Polygon filling. We just talked about the problem with backface culling, that it's not a general solution. So how do you make polygons look more solid? Well, you paint them or fill them. First thing is that you need to realize that we are going to be painting our polygons in display coordinate space. So the polygons that we're going to be painting are actually two-dimensional, flat polygons, because we will have already converted to two-dimensional display coordinate space. We're doing this because even though we don't have access to the pixel level of the frame buffer, essentially we are drawing on the canvas, which is essentially the frame buffer, and we are treating it at the pixel level because we have create line, X, Y, and actually there should be a plus here. So that's how we're going to draw our polygons. We will, or actually draw our pixels. We will draw them one pixel at a time. Okay. So you basically create a line that's one pixel wide. And of course, there's no plus on the Y, Andrew, because we are drawing a horizontal line one pixel wide. If you added one to the Y here, you would be drawing a diagonal line. We want to light up a pixel. So from XY to X plus 1, comma Y, 1 pixel. Okay? Blah, blah, display space. The next thing we need to say is, this is a blast from the past, but we need to go back and say, okay, Mike, what do you mean by polygons? Well, our polygons are defined such that the edges never cross. And we covered this in like lecture 2 or 3 or something like this, where we said a triangle is a polygon in this class and a rectangle is a polygon in this class, but this thing is not a polygon. Now, you could build something that looked at like it out of 2 triangles, one upside down, one right side up, but this thing with the crossing lines is not a polygon in this class. Now, mathematicians would say that this is a complex polygon. Polygons in which edges cross, mathematicians call complex polygons, and polygons in which none of the edges ever cross are called simple polygons. Mathematicians call them that. So we're limiting ourselves to simple polygons and excluding complex polygons. We want to speak like a mathematician. Our fill algorithm will also be limited to convex polygons. You might remember from, I don't know, elementary school or junior high, hell, I don't know when you guys first cover this, that there are convex polygons and there are concave polygons. And so this is a concave polygon, this thing here. So what makes something a convex polygon? Simple polygons are convex if all of the points on any straight line drawn between 2 edges are within the interior of the polygon. So like if I draw a line from here to here, all of the points between these 2 edges are inside the polygon. If I draw a line from here to here, if I draw a line from here to here, all the points are inside. In all of these shapes, that's true. But if we look at like this shape here, if I draw a line from this point to this point, the line will go outside the polygon. Or if I draw a line from here to here, it can go outside, right? Or from here to here, it's inside, 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 outside, outside, inside, inside, right? We don't want to deal with all of that complexity. You can write the algorithms that deal with that complexity, and I have taught it in decades past, but it's much simpler and much more straightforward if you say, look, realistically these days, systems generally use pyramids or use triangles as their basic polygon, because everything can be built out of triangles. I want to keep things a little bit more general because sometimes it's actually easier to use rectangles occasionally, like for the bases of our pyramid or for the faces of our cubes. It's just a little bit more natural to draw those things using rectangles or squares. So I want our polygon fill algorithm to work on both triangles and rectangles. It's a little more general, and it's a little nicer. But I don't want to worry about friggin' lines that cross or things that you can start on the inside and then go to the outside and then go to the inside. I don't want to worry about any of that. So if we keep ourselves to simple convex polygons, that will mean that when we draw a polygon, like this polygon here, we will only have to worry about drawing between two edges on any particular fill line of the polygon. So when we think about these polygons here, we're going to fill them a horizontal line at a time. So it doesn't matter as long as the polygon is simple and it is convex. Even if you've got something like this that's got, what, eight edges to it, you will only be filling between two edges at any point in time, and you will know that you will start at the left and you will go to the right. You wouldn't be able to do that if we had concave polygons, because if I want to draw from this edge to this edge, it's problematic because I've got to draw from this edge to this edge, and then I've got to draw from this edge to this edge, and all four of those edges can be active at one time if we're thinking about slicing this as a horizontal line by a horizontal line. And that vastly complicates the algorithm. So screw all of that. We will stick with simple convex polygons, because in reality we're only going to be interested in triangles and cubes, or triangles and rectangles. Okay? Okay, and what I'm trying to say is it simplifies the problem a lot, because when you consider the edges, you're only going to be drawing between two edges, and there can only be two active edges at one time. Okay, so polygons are generally painted from top to bottom, horizontal line by horizontal line. These horizontal lines are filled a pixel by pixel, a pixel at a time, working from the left edge to the right edge. And by top to bottom, we mean the polygon will be filled from the points that are closest to the top of the display window down towards points that are towards the bottom of the display window. Now, since our display coordinate system is usually located 0, 0 in the upper left-hand corner, with increasing, so X will, so X will increase as we move to the right. That's nothing new about that. X will increase as we move to the right. But as we move down, the Y value is going to go up. As we move towards the bottom of the image window, of the image, of the canvas, our Y's are going to increase, because we will have translated this thing into display coordinates before we draw it. Now, why are we drawing? You might say, it makes things complicated. Can't I just draw it in, three-dimensional? Well, no. You can't fill the flat polygons on the screen if you stay in 3 dimensions, so you got to project it. And then you're like, well, but even if I projected it, can't I stay in projection coordinates? Why do I have to move to display coordinates. The reason you have to move to display coordinates is because in the end, what you're doing is you're setting pixel color values in an array, and that array is turned into an image. It's an image buffer. It's drawn on the canvas. So that's what you got to do. You got to set pixels, and each pixel is really at some row and column of this block of memory that we're calling an image array or an image buffer. And so as you move down an array, right, you move from row to row, and that's going up. So you've got to get things in this system to be able to effectively fill. You might also say, well, Mike, when we drew the outline of our polygon, we drew our edges, right, you know, from B to C, and then from C to A, and then from A to B. We drew them however we wanted. We didn't worry about horizontal lines. So couldn't you fill this polygon with edges that went in any direction? So say, couldn't I fill it with diagonal lines and just draw them like that? Well, you could. It would be a hell of a lot slower, and you would see little holes show up in your painted polygon. Why would little holes show up? Little dots would show up that aren't painted right. Well, because you would be getting round off error if you try to draw this, because your points exist in some three-dimensional space. When they're projected here, they have to be rounded to particular pixel locations, right? And so when you're dealing with rounded values in particular pixel locations, and you're trying to take a line and trying to take a slope and deal with all of that, you're going to get round off errors. And so we want to make sure that there are no little Swiss cheese effect of holes in our filling. And the way we do that is we fill one row of pixels at a time. We used to call these scan lines because the old-fashioned raster display that we talked about on like day 1 or day 2 would actually draw, remember, would actually fill a scan line at a scan line. It would scan through the image. Well, we don't have scan lines anymore, but we still have an image that's composed of rows and columns of pixels. So the most precise way that we can fill it, and the fastest way that we can fill it, is to move through the polygon a row at a time, a line at a time. And so that's what we're going to do. We're going to be considering a line at a time, and then we have to ask ourselves, well, you know, on this line, if I have some arbitrary line here, how do I know where to start filling and where to stop filling? Well, that's given by the edges of the polygon. So I'm going to be moving down a row at a time, a line at a time, and the decision will have to be, where do I start filling and where do I stop filling? Algorithmically, we have to determine that. Since we're using simple convex polygons, I'll know that there can only be 2 active edges at a time. If I'm looking at a scan line right here or a fill line right here, the active edges are BA and BC. Now, when you get down to here, right, when you go to the next scan line, it switches between drawing from BA to BC to AC to BC. So the edges can switch. That's one of the most complicated pieces and one of the most delicate pieces of our scanline algorithm is how do we deal with the edges switching? Okay. All right, but before we talk about edge switching, let's try to think about how we can figure out where to start and where to end filling on a particular scan line. Well, edges have slopes, right? So the edge BA has the slope of the end X is or the end Y and the end X. So if we look at, let me scroll down here and show you. Edges have slope, and slope is defined as Y end minus Y start over X end minus X start. Okay, so that if we want to look at our edges, like BA, right, we have to have the Y end, which is 20, minus the Y start, which is 0. 20 minus 0 gives us 20, over the X end minus the X start. The X ends at 10, and it started at 30. 10 minus 30 is minus 20. Minus 20 divided by minus 20 is minus 1. The slope of this line is minus 1. We can compute the slope of line BC. Well, the slope of line BC is infinite because it's a vertical line. Vertical lines have infinite slope. You try to use the slope equation and you subtract your x's, 30 minus 30, that gives you 0. You're doing the divide by 0, so you're getting an infinite slope here. So that's something we have to think about, worry about maybe. And the edge AC, well, its slope is 1/2 because its y is 30 minus 20 gives us 10, and its x is 30 minus 10 gives us 20. 10 divided by 20 is 0.5. Again, I wrote the equations down here at the bottom of the page. It's just yn minus y start over xn minus x start. But there's the math. Don't get scared. The other thing you might have noticed is that I said that the line from BA, normally when we talk about drawing an edge, we say, well, A to B, B to C, C to A. All right. Why am I calling this edge BA rather than edge AB? Because edges are defined from the vertex with the smallest y to the vertex with the greatest y. Because we're going to be drawing our lines, our polygon, from its topmost vertex down. So the edges have to be drawn downward, right? This is edge AC because A is higher than C. What do I mean by higher? I mean it has a smaller y value. So this point has a y value of 30. This point has a y value of 20. This point has a y value of 0. And this whole polygon that consists of 3 edges and 3 points, point B at 30, 0 is the point, the vertex with the smallest y. It is the x minimum in this polygon, the y minimum, the most vertical. Point C is the y max because it's got the biggest y value of any of the points. Remember how I said that we were going to paint fill lines, right, vertically, starting at the top and going to the bottom? Well, it just so happens here that this point starts at 0. But let's say we had taken this thing and we shift it down 100. That's fine. We would, instead of starting at row 0, we would start at row 100. And instead of ending at row 30, we would end at row 130. So basically, we're going to do our fill, our range of filling will go from y min to y max, where y min is the minimum y value of all the vertices in the polygon, and y max is the biggest y value of any vertex in the polygon. That gives us the range of fill lines that we have to be concerned with. And in fact, that'll be how we run our outer loop in the algorithm. Okay. All right. So we're going to be painting from the y min to the y max. That's going to be our which edges we're interested in, or which lines, fill lines we're interested in. How do we know where to start and where to end? Well, we've noticed that edges have a slope, but slope is rise over run, as we learned, way back when we were in junior high. But we don't want rise over run. We're going to move in y at a fixed rate. We're going to move down one scan line each time. So every time we move from one fill line, sometimes I call them scan lines, to the next fill line, we'll be adding 1 to our current y value. We're adding 1 to our current y value. So the y change is fixed at 1. We need to know the corresponding x change on the edge, on the active edges, for a fixed 1-point change in y. So we're going to take this slope equation and we're going to flip it over to get the inverse slope. This inverse slope will be called dx, and it is the change in x per a change of 1 in y. So it's the change in x over the change in y. So now then if we look at, this is the top of the same thing that we were looking at a moment ago. Point B is at 30, 30, and if you go down to A, it would be where it was, and C is still where it was. So these are still the edges. And here are the slopes that we computed. We said that this was a slope of -1, and this was a slope of infinity. Well, we're not really interested in the slopes. We're interested in the inverse slopes. So the inverse of 1 over -1 is -1 over 1. So this still stays -1. But this goes from infinity. When we flip it over, it goes to 0. So vertical lines have a dx of 0. What does that mean? That means if you're thinking about filling these things a line at a time, every time I go down a line, I'm increasing my x for this edge by 0. It's not moving, right? But every time I move down a scan line here, my dx is -1, so I move back a point in x. So this is point 30, 30. This is point 29. This is point 30, 0. This is point 29, 1. This is point 31. This is point 28, 2. 29, 2. 32. This is point 27, 3. 28, 3. 29, 3. 33. So we're going, our y starts in this case at 0, and then it's 1, and then it's 2, and then it's 3, and then it's 4. You can see it's a loop that's increasing by 1 each time. And what I need to know is I need to know, okay, based on where I'm starting, how much do I have to change my x each time I move down a scan line, down a fill line? Well, that's the inverse slope, in this case -1. So every time I move down a row, I subtract 1 from the x value of the previous value for this edge. So it's 30, 29, 28, 27, 26, 25, 24, because I'm moving backwards and my x's here as I'm moving down. How much do I add each time for edge BC? Well, it's vertical, so I'm moving 0 each time. So it's 0, so it's 30 is the x value here, 30 is the x value here, 30 is the x value here, 30 is the x value here. Am I making some sense as to how this is working? So we're scanning our lines vertically, and the dx is telling us how to change the start and the end point. Okay, so that's dx. Now, what are the equations? Well, the equations are like you would expect. You have an equation for your left edge, and you have an equation for your right edge that gives you dx, the inverse slope. And it's still end minus start in x, x end minus x start over y end minus y start. But I have these little subscripts that say, oh, I'm dealing with the left edge here. And that gives us the dx for the left edge. And how do you know where to start? Well, your starting point for x is going to be the x start value for the left edge. It's the x component of the starting vertex for this edge. And then how do you know how to change the x each time you move down a fill line? Well, the left edge x value at fill line I+1 is the x left edge value at fill line I, the previous one, plus the dx for the left edge. So basically, every time I move, every time I move down a line, I take my previous x and I add my dx to it, and that gives me my new x value for the next line. You do that for the left edge, you do that for the right edge. These are exactly the same equations. I just changed edge left to edge right. Okay, so that gives us the starting x value for each edge, because my x on a fill line at first pixel 0, is going to be the x starting on this fill line. And then as I move across, I'll just add 1 each time. So like I said, if we're starting here at, that's 28, 20, this is 30, 29, 28, 27. So if I'm starting at 27, 1, 2, 3, at 27, 3, then it's 28, 3, then 29, 3, then 30, 3. So each time I'm just adding 1. And that really is the core algorithm there. Now, we'll talk some more about this. I'll go through that. I'll talk about pre-computing a fill table. I'll talk about some blah, 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 and then I'll give you the actual algorithm here for fill. And then you might say, well, Mike, you only got halfway through fill. Aren't you supposed to do the Z? Well, Z is going to turn out to be equations that are almost identical. And the only difference between fill polygon and adding Z buffer is what I have in green here. So it's, 10 lines that I had to change to add Z buffering to polygon fill. Questions for me? Go ahead and get started yesterday. Even if you're fuzzy on fill, that's fine. You've got 2 days worth of work that you can do on getting backface calling working right now. And we will go through the rest of polygon fill on Friday, and we'll go through Z buffer Friday. Once you understand fill, Z buffer is very, very similar. Are there any questions for me? And yes, subscripts to subscripts to try to keep everything, but I did that to try to keep everything straight, because you're dealing with 2 active edges and then a fill line that goes across. So we're juggling some balls here. Okay, gang. If you have any questions, I'll be happy to stick around after class. Other than that, I will see you guys on Friday. Have a good day. I'll talk to y'all later.